area of a rhombus and area of a kite. These are the last two figures that we're going to be working with. So let's talk about what a rhombus looks like. So this right here is a rhombus. It looks like a square that's been sort of squished over. So all the sides of a rhombus are equal to each other, very similar to a square. So all sides are congruent. And like our friend the parallelogram, it's similar in that its opposite angles are congruent to each other. Okay? So opposite angles are also congruent. And also, like our friend the parallelogram, the angles along the sides add up to each other. So the two angles beside each other add up to 180 degrees. So A, B, C, D. I could do them all. A plus B equals 180. B plus C equals 180. D plus C equals 180. And A plus D equals 180. So those are some very important things about a rhombus. The most important thing about a rhombus, though, is that they have these two things called their diagonals. So this segment AC and segment BD, those are called diagonals. So AC and BD are diagonals. Here's what you need to know. The diagonals are bisected into two equal parts. So diagonals. Number one, bisected into two equal parts. That's what bisected means. Okay? That's what dissected or bisected means, two equal parts. That means that this segment equals this one, and that this segment is equal to this one. So we cut them into two equal pieces. The other thing about the diagonals that are important is that they form a right angle. So they form a right or a 90-degree angle. So that's also really important. So you're going to get a four-way intersection here of 90-degree angles. All four of those are going to be 90-degree angles, okay? So important information about the rhombus. So this side is the rhombus. Now, before I give you the formula, let's talk about the characteristics of a kite. So over here, I have a kite. You'll notice that these two sides are equal to each other and that these two sides are equal to each other, okay? And usually they're symmetrical. Usually you can draw a line right down the center of them and you are able to see that they share a side. So let me draw in the two diagonals. So I have this diagonal and this diagonal. So again, the diagonals on a kite have a characteristic where they cross to form a right angle. Okay. So they form a 90-degree angle. That's important. We have our 90-degree angle in there. Okay. And these two segments, or these two parts, are often congruent to each other because the kites are usually symmetrical. So typically those two will be equal. You'll notice that these two, the two upright ones, are not. Obviously the top piece is much shorter than that longer bottom half. So that one's not broken into two equal pieces. But the one going horizontally is. So the formula for this, the formula for the area of a rhombus and a kite is 1/2 diagonal 1 times diagonal 2. So again, we're doing half of some sort of an area happening here. So let's talk about why this is occurring. And I'm going to do that down in this blank space. You can maybe do it off to the side or somewhere on the page where you have space and draw an arrow. I'm going to do it right down here where I have a little bit of space. Okay. So what I want to draw for you is this. So here is a typical rhombus. Okay. And this works for kite as well. I have all my sides equal, okay? So in order to solve this, I need 1/2 diagonal 1 times diagonal 2. So if I draw in diagonal 1, let me draw it in green, okay? I'm basically saying that this, sorry, that's not where I want that. I'm basically saying if I draw this square around the figure, right? If I do this, then I'm saying, whoops, that this diagonal 1 is the same as this. So this is the same distance. We'll call that diagonal 1. It's the same length, right? And if I do it in a different direction, and this time I'll use like a weird pink color, if I do this diagonal, right, then I can say that this is the same distance. We'll call that diagonal 2. And so if I wanted the shape or the area of this entire black square, right, that would be base times height for the whole square, and that would be diagonal 1 times diagonal 2. It's the same thing. I would do the length of one side times the length of the base, and I would have the area of the whole thing. The problem is I don't want the area of the whole thing. I want to get rid of this, which is exactly the same as this triangle, okay? And I want to get rid of this, which is exactly the same as this triangle, and I want to get rid of this, and I want to get rid of this. So basically, I only want out of the, let me count them for you, 1, 2, 3, 4, 5, 6, 7, 8 symmetrical triangles. Out of all 8 of those symmetrical triangles, I really just want these 4, right? I want those 4 triangles. So I only want half of that. So that's where the formula comes from. I only want half of the square that would be formed if I overlapped those triangles, okay? So hopefully that makes a little bit of sense. Let's just try a couple. So I'm going to give you this 15, okay? And let's see, what else do I give you? Oh, and then I'm going to draw in my diagonals, and I'm going to tell you that this segment right here is 12. And I want to know the area of that particular rhombus. So here's a problem. I can tell you that this diagonal, we'll call it diagonal 1, is equal to 24. Because remember, I know that my diagonals are bisected into 2 equal parts, so that means this one has to also be 12. So diagonal 1 is 24. The problem is I know absolutely nothing about diagonal 1. So I have to figure out how am I going to find some information about diagonal 1. Here's what you do. You use what you know about triangles. If I redraw this, and I tell you that this is 15, and I tell you that this is 12, the other thing we learned about diagonals, aside from the fact that they're broken into 2 equal parts, is that they form a 90-degree angle. So I know this is a right angle. So I can put that in here. And I'm really looking for, can you tell me how long this segment is? That would be this piece. Then I can double it, and I will know what diagonal 1 is equal to. So we're just using what we know about triangles. That's a right triangle. How do you find the side length, a missing side length of a right triangle? You use the Pythagorean theorem. C squared equals a squared plus b squared. So the c is always the hypotenuse, so 15 squared equals x squared plus 12 squared. Okay? So 15 squared is 225. Sorry, I'm running out of space. Equals x squared, and 12 times 12 is 144. And to get x squared all by itself, I have to subtract 144 from both sides. If you do that to one side, you got to do it to the other. So then I get 81 equals x squared, and we've talked a million times now about how do you undo an x squared term. You square root it. So the square root of 81, and you're going to square root the x squared. So x is going to equal 9. So now I know that this side is 9, so I can label it here as 9. And I know that they have to be equal because they're bisected. So diagonal 1 is 24, and diagonal 2 is, or diagonal 1 is 18, and diagonal 2 is 24. So if I know both of my diagonals, I can now use my formula. Area equals 1/2 diagonal 1 times diagonal 2. Multiply those all out. 18 times 24, then take half of it, and we get 216, and we'll call this meters squared. I didn't give you the label in the beginning, but let's just say that these are meters, so meters squared. So again, using information we learned about our triangles. Pythagorean theorem, we used 30, 60, 90 for the trapezoids. So that triangle stuff will never go away. It will always stick around. You'll see it again in Algebra 2 as well. You'll see it again in pre-calculus. So you're going to continue to see your triangle information. Keep that stuff handy. Keep those notes handy. If there are certain things that you can't remember, like what your 30, 60, 90 or 45, 45, 90s are, or the Pythagorean theorem, put some examples, 3 little examples on a note card, and keep it in your folder so you can just pull that out and reference it when you need it, and you don't have to fiddle through all your papers and notebooks. All right, let's look at example 2. So this time I'm going to give you this figure. Okay, I'm going to tell you that this is 5. I'm going to tell you that this is 2. And I'm going to tell you that this is 3. And these are all meters. Okay, so we're doing this in meters. So now what I need you to do is tell me what is the area of this particular kite. So area is going to be 1/2 diagonal 1 times diagonal 2. So we're multiplying these all together. So this diagonal has a total of 5 plus 2, or 7. So we'll call that diagonal 1. And then diagonal 2 has 3 here, but we also know that this must also be 3, because we know those are broken into 2 equal parts. So diagonal 2 equals 3 plus 3, or 6. So I have diagonal 1, which is 7, diagonal 2, which is 6, times 1/2. So 1/2 times 7 times 6 gives me 21 meters squared. So there is the formula for the area of rhombuses and kites and how to solve them. Please make sure that you are asking. If you need to review some of your triangle stuff, please ask about that. We'd be happy to help you.